Oi. Hello there, it's Mr. RD with another Java video, and this time we're looking at sorting. Our goals here are basically just to first be able to implement a number of different sorting algorithms using Java, and then a secondary goal is to learn how you can use the Java API to simplify sorting for you. And we're going to kind of cover both of those topics. So, in many times in programming, you're given a task to sort something. And very often I'll give my own kids, I'll say, look, I'm tired of your Lego everywhere, sort it. And they have a bunch of bins. And the first thing you have to realize with sorting is that there isn't one way to sort things. There's a number of different strategies that you can use. Some people would prefer to sort their Lego by color. Other people would sort their Lego by the size of the piece, or a combination of the two, or perhaps they'll look at flat pieces and then thicker pieces, or perhaps they'll put all of the weird pieces in one bin and then look at the other pieces in some other way. So when you're being asked to sort things, there's two kind of things you need to think about. One is what categories or what criteria are you using to do this sort? And that is very separate from the other side of things, which is looking at what technique am I going to use to help me sort. So if I decide that I'm going to sort this by color, am I going to look for all the green ones first? Or am I going to just take this and make a smaller group and sort that smaller group and then grab another set and then sort that smaller group and so on. And so on one side you have to decide what criteria am I going to use, and on the other side you need to think about, okay, what's the strategy I'm going to use to actually sort these based on the criteria that I have chosen. And so what we're going to do is we're not going to be able to address the criteria piece, because that differs depending on what it is that you're trying to sort. You're going to sort Lego differently than you're going to sort playing cards, which you're going to sort differently than you're going to sort robots or fractions or something like that. What we're going to focus on is the different strategies we use, and these strategies will be applicable for all sorts of different criteria. Ascending, descending, all that sort of stuff. And as we go through these, we're going to start with very simple sorting algorithms, and we're going to move on to more complex ones as we go through. And the very first one we're going to look at is called selection sort. And selection sort is one of what we call the quadratic sort techniques. And what I mean by that is that the efficiency of this algorithm is going to be essentially an n squared, a big O of n squared. So let's have a look at how this works. So here we have a trusty set of playing cards, and what we want to do here is to sort these playing cards, and we want to sort them in an ascending fashion. So the way that selection sort works as a technique is it's going to have a loop that is going to loop through this entire list of cards looking for the lowest number. So it's going to come here, it's going to say 8. 8's the lowest so far, I like it. King, nope. Queen, nope. 4, oh nope, that's the lowest one so far now. 6, 7, it's reached the end of the list. It knows that 4 is the lowest, so what it's going to do is it is going to swap the 4 and the 8. Now it's going to, the loop is going to come to the next item, and it's going to start here and go all the way to the end of the list, and it's going to look for the lowest one. King is the lowest, queen is the lowest, 8 is the lowest, 6 is the lowest, 6 is still the lowest, so it is going to swap these two over here. Now the for loop advances to the next item. It's going to go down to the end of the list, and it's going to look for the lowest one, which is the 7. Do that again, it's the 8, so there's no swapping necessary. Do that again, it's the queen, and now we have a sorted list. Looking at that with just numbers, you can see what's happening here is that the first time it runs through the list, it's going to swap these items. Then it's going to start at the next position. It's going to go through the list. It's going to find the lowest, which happens to be 1. Nothing is net required. It goes to the next one through the list. 2 is the lowest, so it swaps those 2. You're going to notice this theme again and again with the sorting, is that there's the searching for something and then there's the swapping. Those are key operations. We've got searching, swapping, searching, swapping. In this case, you can see why it's a quadratic efficiency. It's essentially just a nested for loop, and it's going to start here and it's going to run through the rest of the list. And then your outer for loop moves up by 1 and it goes through the rest of the list. And then the outer for loop moves up and then the inner for loop goes through the rest of the list. So we've got 2 for loops and they're each running through everything in the list. But by the end, you can see that you will end up with a sorted list. So if we were to break this down into with pseudocode, okay, we can look at the selection sort. You know that you're going to have a list. It's going to have a certain length, and you have one loop that is going to go through the entire list, starting with the first item and going right till the end. Then inside there, you are going to have something that has to find the index or the position of the smallest item. In this case, we've made it a method, but this could easily have just been a for loop inside here. And the for loop is not going to start at the same position. It's going to save a comparison, and it's going to move one over. And so it's going to start with the next one. It's going to go all the way till the end. And it's just going to keep track of which index has the smallest item. That's all it's really doing. Then over here, we're just going to swap them. Now, there's certain efficiencies that you could find here and there of only swapping if you need to or something like that. But essentially what's happening here is I have a for loop that's going n times and another for loop that's going n times. And so it's a quadratic sort. There are going to be exchanges in this sort of naive algorithm. There are going to be n swaps taking place. One for every item that you search. There's going to be a swap taking place to ensure that the lowest item is there. So how do I think of this algorithm? I think of this algorithm as it's sorting from the bottom to the top, such that as I go through, I'm building a small sorted list of 1, and then a sorted list of 2, and then 3, and then 4, and then 5, but it's starting with that bottom and it's moving its way up to the top. The next algorithm I want to look at is something called bubble sort. And it's called a bubble sort because think about like a bubble in a drink, let's say. And it might start at the bottom, but by nature of being a bubble, it's going to rise to the top. And the bubble sort works almost in an opposite way of the selection sort. The selection sort starts sorting at the beginning. The bubble sort is going to always push the highest number over to the top, so that you're actually sorting in the opposite manner. You're going to sort starting with the highest number and moving down to the lowest number. We're going to jump over to our example again. So here we've got our set of cards again, and we're going to look at them. And what we're going to do is we're going to treat these 2 cards as a bubble. So you can think of it as like a bubble or a window, and that bubble is just going to keep moving to the right. And it's always going to be looking at 2 cards, and it's going to figure out which one is the biggest and then potentially swap. So let's look at these 2 cards. This is our window to start. Because the queen is larger than the 7, we are going to swap these 2 cards like that. Now the bubble moves over by 1, right? For loop. It moves over by 1. It's going to look at these 2. And the queen is bigger, so it's going to swap these 2. Bubble moves over again. Queen is bigger. It's going to swap these 2 here. The bubble moves over. The king is bigger. Nothing is required. The bubble moves over. Now, a couple things that are different here. Number one, of course, we now have the biggest card at the end, which is what I said would happen. But The behavior of this is a little bit different. Because we've been doing all of these swaps along the way, we've actually sorted a little bit more what's happening. You'll notice that the queen also is in a better position than it was before. And so there's a little bit of extra sorting going on as we're moving through. There's also a lot more swaps happening for each iteration. But it's going to get less and less as we go through, and it's possible to have a sort done before we've iterated through all n times. So we come through here, we're going to do the swap with this. We look at this now, we're going to swap these two. We're going to come here, nothing is required. We're going to come here, and we swap these two. Now we've only gone through this twice so far, and yet I have a perfectly sorted list. And so the next time that I go through this, I'm going to come here, nothing to swap, here, nothing to swap, here, nothing to swap. I already know this is done. I don't need to loop all the way till the end. Once I've gone through this and had no swaps, I can just stop. I can end my for loop prematurely and say, I'm done. We're good. And so you can see this happening in a different way here of the swapping that's going on. And so it will check and it will do a swap if necessary to keep pushing the larger ones towards the end. And so after one pass, the largest item will always be at the end, and the next time you go through it, you can ignore this item there. Here's another example, 5, 1, 12, negative 5, 16, and you can see it's going to swap, nothing to swap, swap, nothing to swap, and then it will go through. So bubble sort is really neat, and it is still considered to be a quadratic sort, but I think you can see that its behavior is different than the selection sort. It will be much more efficient with certain sets of data. It's especially great when the data is close to being sorted to begin with. It still has a worst case, right, as a quadratic, but it does have some best cases. So if it's already sorted, then it only needs to run through once to know that. Right? It only needs to run through once and say, I didn't have to do any swaps. We're good. We're done. So best case is pretty good. Worst case, however, the worst case, we're not. You still n squared. Can't avoid that. But the fact that it provides some benefits at the beginning potentially makes this a different sort worth learning. The algorithm is a little bit different. You could still use a for loop and play around with it. You guys know for loops and while loops and do loops are interchangeable. But what this is going to do is it's going to keep looping as long as something has been swapped. As long as something inside here has been swapped, it's going to keep looping. But the minute that I've had to do no swaps, I'm out of there. Don't need to worry about it anymore. And then the inner loop here is going to start at position 0, always at the beginning, and it's always going to go to the end, but it's going to kind of always ignore as it moves across. Okay, the efficiency of this could be improved a little bit. As you go through your swapping, you could potentially continue to ignore more and more of the one side of your list if you wanted to. Okay, so the next one is insertion sort. And insertion sort is what most people do when they play a game of cards. Is you usually have your cards, which you've sorted already, and when you pick another card up, you are going to take that card and you are going to place it in the correct spot. You are inserting a new card, and you are going to go through your cards until you find the spot where it fits, and that's where you're going to fit it. And that is essentially the way insertion sort works. Again, I'm going to demonstrate it for you in a couple different ways. Alrighty, so insertion sort. So the way that insertion sort works, this is another one of those quadratic efficiency sorts that's going to behave a little bit differently than the other two. And so what that means is ultimately this is going to be driven by two loops. So the first loop is going to start with the first card. And it's going to look at this first card, and then it's going to look at all the cards before it, which there are none. Since there are no cards before it, this card is in the correct place, and we just put this card, we're done. Then the loop moves over to the next card. And what it does is it loops backwards towards the beginning of the list. And it says, okay, is 8 bigger than 6? It is. So we're going to move this 8 over. We're at the beginning of the list. So I'm just going to insert this into the correct spot. Then it moves over 1. And it says, all right, let's fit king into the right spot. It moves backwards. It says, is 8 greater than the king? No, it's not. So it's going to just put this back where it is. Then it's going to come over to the 4. And it's going to have a loop that's going to keep going back. It's going to first look at this card. It's going to say, is the king bigger? You darn right it is. Is the 8 bigger? You're darn right it is. So it moves the 8 over. Is the 6 bigger? You're darn right it is. So it moves it over. It's reached the beginning of the list. So it sticks the 4 in where it belongs. Comes to the queen. Starts looping back through the list. Is the king bigger? Yes, it is. Is the 8 bigger? No, it's not. So I can stop right there and insert the queen into that position. Now the loop moves over one more, and it's going to look at this, and it's going to say, okay, is the king bigger? Yes, it is. So it's literally, right? It's moving the king over one position. The queen bigger? Yes, it is. It moves it over one position. Then the loop goes back again. Is the 8 bigger? Yes, it is. So it moves it one position. Goes back once more. Is the 6 bigger? No, it's not. So it takes that 7 that it's pulled out and throws it into the correct spot. And because I've reached the end of my list, I'm done. I have a sorted list of cards. And that's the way this algorithm works. Is it's going to find the card that it's looking for, and it is going to search backwards through it until it finds the correct position for it to go into. Here, let's look at another example. It comes here, -5 needs to be inserted. The 7 is bigger, so it moves the 7 over. Then because it's reached the beginning of the list, it inserts the -5 into here. Then we get to the 2. 7 is bigger, it moves the 7 over. Looks at the -5, the -5 is smaller, so it inserts the 2. Inserts, that's an insertion sort. So in order to do this, you need to definitely kind of pull the value you're looking at out of the list temporarily, right? Just a variable that holds that, and that will allow you to move the items along, and then you insert this back in. Another way of looking at this is if you think of a deck of cards, you're looking at first a hand of just one card, and then you're adding another card into it, and then you're adding another card into it, and then you're adding another card into it. You do not need to create a second list here. You're still using only your one list. You're just temporarily pulling an item out and then figuring out where it fits into the smaller list around it. Insertion sort is another n squared, as I mentioned. In the best case, the number of comparisons it's going to have to make is linear. But the number of shifts is one less in this case than the number of comparisons that it's going through and having to make. So what we've done so far is we've talked about the quadratic sorts. And you know from our talk of Big O notation that we can look at best cases, worst cases, and average cases. And so when you look at the worst cases, all of these sorts are quadratic sorts. But what's happening is that each of these sorts have a different set of best cases. And when you look at the number of exchanges being taken, right, you can look at the number of comparisons, greater than, equal type of things, versus the number of swaps. They also have a different look. So you can see now, if you say, under what situation would selection sort be better than bubble sort? Well, you see it's not this situation, not this situation, not this situation. Really, it's only when you look at the worst case for number of exchanges that selection sort could potentially be be better. And so you can see that there'll be a scenario or a case for each of these types of sorts. There are other types of sorts that we look at. There's something called a shell sort. And a shell sort is going to have a slightly better big O notation. Instead of n squared, we're looking at n to the power of 1.5, which is a little bit better. And it's called a shell sort simply because the person who discovered it, his name was Shell. And it uses kind of a divide and conquer approach. And what that means is that instead of trying to sort the entire array, what if we tried to sort smaller arrays instead? And so you can, instead of having to worry about inserting a card into the whole thing, what if we just divide it in two, let's say, and insertion sort this, and then insertion sort this, and then take those two lists and merge them together. And so if you do something like that, that might assist, and it does, in fact, assist in the performance. The problem is, how do you choose the gap or the division? And as we talk about these other types of algorithms, we're going to talk about merge sort next and quick sort, is that one of the tricky parts is deciding what sort of gap or what sort of division you're going to make in order to get these sorts to work. So merge sort is another way of doing it. It's a very similar idea. And what it does is you're just going to continue to break up the data into categories. And this is the first of our what's called recursive sources, which means recursive sorts, which means it's going to do the same thing over and over again in a recursive fashion. It's going to look at the whole list, and then it's going to look at part of the list, and then it's going to look at part of that list, and it's going to look at part of that list. And what merge sort does is it takes the big list, cuts it in half. Then it takes that list that's been cut in half, and it cuts that list in half. And it's going to continue cutting in half and cutting in half and cutting in half until it gets to just one item. And once it reaches that one item, it knows that it's sorted, and it goes back up and it looks at the next item and it just starts placing them together. We're getting to the algorithms that are harder to explain, so I'm going to try to just visualize it again for you. So what it does is it takes a list, 6 cards, and it's going to break it up into 2 lists of 3 cards. 2 lists of 3 cards is a lot easier to sort than 6 cards. It takes fewer operations, remember, because we were dealing with quadratics, so this is going to take fewer operations. Well, what if we further divided this and we broke it up into cut it in half so that I had 1 card and 2 cards. And I could also, if I wanted, cut this in half. I look at my king is already sorted, no problem. I look at these, well, I could break these up into individual cards. It's not really going to help, but each of these individual cards is sorted. Then once I go in and recurse or go back up, it is just going to join these together like that. And then when it comes back up and it wants to join these lists back together, it is going to join them by putting them one by one back into the list in the correct order. Then it's going to come to this side. It's going to look at the queen is sorted, it's going to find the 4 and the 7 by themselves, and then when it wants to merge them back together, it is just going to merge them one by one, taking the 2 sides. Then we're coming back where I'm back to only having 2 sets of cards, and so it's going to merge these back together, and it's going to have the 4, the 6, oops, that's not good, the 6, the 7, the 8, the queen, and the king. Did you see how that merge operation was working there? So when I have my 2 lists and I want to merge them together, it basically just looks for the smallest one from either list and it inserts that in there. Then it finds the next smallest one and puts that in there, and the next smallest one and puts that in there, and so on and so forth. The key here, and I should have changed that, this is the merge sort. The key here is that it keeps splitting and splitting and splitting. Because when you're dealing with a quadratic type of operation, looking at 10 is much, much worse than looking at 5, which is worse than looking at 3. And so what it does is it splits and splits and splits, and then in the end it merges together by looking at the splits and just saying this one's smaller, this one's smaller, this one's smaller, this one's smaller, and then it's a nice quick N operation to just come through and get everything in the place that it needs to. So it's a bit of a trickier one to get your head around, and the algorithm is also a little bit trickier. In fact, I haven't really taught you yet what you need to know to fully be able to implement this on your own, because it is the first of what's called a recursive algorithm, which is basically an algorithm that calls itself. Think of a method that calls itself from inside the method. And that's coming up in a topic very, very soon. But I just wanted you to understand the general technique of how this particular sort works. So you can see here what's happening is it's going to split the two lists, and first it's going to look at this one list. It's completely ignoring the other half. And then it's going to take this and it's going to divide it again. And so now what I've got is I have two one-element arrays, and it can just merge these back in together. Now it looks at the second list that it's divided it into. It looks at each of these separately, merges them in together, and then now I have a 50 and a 60, a 30 and a 45, and it is going to merge these two together by saying, is 30 or 50 smaller? 30 is. What about 50 and 45? 45 is, and then 50 and then 60, and now I've got this half nice and sorted in. And I've done it with a certain number of operations. This, the problem with merge sort can be that it's the subdividing of lists that can take storage and could also take time to have to subdivide it. You need to find a nice efficient way to be able to deal with all of these little sublists that you're trying to create. But it is faster. So it's n log n, and we already talked about how log n is considerably, or can be considerably faster than n. So an O of n log n is great, but it is requiring a little bit of extra overhead. I do want you to know that there are a couple of other algorithms as well. So one is called heap sort. I'm not going to go into the details of this one, but essentially what it does is it has the same sort of efficiency, but it doesn't require all that extra storage. And instead what it's going to do is it's going to organize itself in a different manner. It's a really cool algorithm, actually. And then the last one that I wanted to go over is called quicksort. And quicksort is a very famous sorting algorithm. It's by default, it's what's used in Java when you have the Java sort method that you use. And it's the same sort of idea here, in that all of these work under the principle of it's going to take less time to sort a smaller list than it is to sort a bigger list. The problem with something like merge sort is that it's a very naive choice. It just says, cut my list in half. Well, what if you have, what if it's sorted in such a way that cutting in half doesn't give you a nice even distribution? Right? What if it's weighted too heavily on one side or weighted too heavily on the other side? What quicksort does instead is, rather than saying just cut it in half, it is going to choose a pivot point. So let's say you have a set of list items between 1 and 100. It's going to choose a pivot point, and that pivot point might be the halfway point, but it might not be. It may be the pivot point is going to be 8, or maybe the pivot point is going to be 92. It's going to choose a pivot point, and it's going to arrange all of the items less than that pivot point on one side and all of the items greater than that pivot point on the other side. And that actually has the potential to offer a lot of efficiency as long as you choose the right pivot point. And that's one of the tricky parts with the quicksort. And quicksort is another one of these things we call recursive, because it's going to find a pivot point, and then it's going to find another pivot point, and it's going to continually use that as it goes through. It's a really neat algorithm. I do want to make sure you at least understand what I mean by pivot point here. And so in this case, what it's going to do is I have this list of items, and it has chosen a pivot point of 44. And so when it chooses that pivot point, it is going to shove everything less than 44 on one side and everything greater than 44 on the other side. And then it is going to look at this list here. It is going to choose a pivot point, and it is going to move everything from that pivot point to one side or to the other. And then it's going to continually do that until it has that sorted list all done. Pivot point, move, pivot point, move. You don't need to worry so much about the merging anymore, because this list is always going to have items bigger than the pivot point. And so when I want to go and bring this back into the sorted list, it's already in order. This automatically fits on this side of the pivot point, and this automatically fits on this side of the pivot point. It's a pretty sweet sorting algorithm. The tricky part is choosing how to find your pivot point, and then how to do that partitioning as you go through. Now, I strongly encourage you to have a look on YouTube for some visualizations of these sorting algorithms, because sometimes they help. I'm just going to show a part of a video of one of these, and it goes through actually different distributions of data, because remember I said how the data is distributed is going to affect which algorithm is better or not. And we're just going to kind of look at the random one quickly. And what you can see here is the different algorithms at work. So merge sort's doing awesome. Quick sort's pretty much done. The selection sort is starting at the bottom and slowly building one by one. Insertion sort is taking this item and finding its correct spot. And when it finds the correct spot, it stops and moves over. The bubble sort, you can see little swaps going on as it comes through. And it's always rising the largest item up to the top. And so with this random distribution of data, you can see that some algorithms are performing better than others. There are some that I hadn't talked about with you, but you can see many of the ones that we did talk about here. Now, depending on the type of data that you have, you're going to get a slightly different view. So let's just look at what's happening. Quicksort's already done. Insertion sort seems to be doing quite well here. So in this case, this is the sort of thing that favors insertion sort finishing well before those. Here's an example of the data being completely reversed. Quick sort, done. Shell sort, done. Merge sort, done. And these ones, oh my gosh, that looks painful. So hopefully that was a good overview for you of the different sorts. I strongly encourage you, you need to have a good understanding of all the first three really well, like the algorithms. You need to be able to identify them. They're very common. They're also very bad sorts. The other algorithms that are starting to rely on recursion, I need you to be able to identify generally how they're working. Do they use a pivot? Are they splitting in half? What's going on? But you don't necessarily need to be able to implement the algorithms at this point, at least. So hopefully that helped explain a little bit about sorting. I will see you again with another video.